Welcome back, everybody. Anybody else a little emotionally drained after?
I don't want to talk about it. Yeah.
Well, not to be that guy, but like
I'm everything drained.
I did call it. Like I knew it was gonna happen. It happens every year.
I suppose you
Keegan,
did.
Shut up.
It happens every year, Andrew.
Keegan, shut up.
Andrew, it happens every year.
Keegan, shut up.
Andrew, it happens every year.
All right, guys, that's enough. I'm wearing black because I'm in mourning from the game. Boy, that was something else. Stuff happens, though, I guess. I was wrong. I totally thought we'd have it.
Three
We
interceptions.
were making a comeback for a second.
Yeah.
Three
Boy.
interceptions.
And you know, that's the hardest loss to take, when it's like you're totally out of it, and then you come roaring back, and you're like, we're going to totally do this. And then it's so anticlimactic.
When you don't do it.
Oh, boy. So, well, anyway. Life goes on, and all that. How many of you guys in here like math?
Oh,
It's actually like my least favorite thing in the world.
Okay.
How was it?
So, why should you never talk to a math teacher about infinity? Exactly. They just go on and on and on about it. Because it's infinity. How many of you in here are in a relationship?
Yeah.
Couple people?
My mom.
Alrighty.
I'm in a relationship with the air.
Why is it that couples rarely go to the gym together?
Because they don't like to do things.
Well, a lot of relationships just don't work out.
That was actually kind of funny.
Oh, good. Number 2 is better than number 1. All right.
That was
Yes.
I'm going to use that
I
one.
have a pun.
Okay, let's hear
You
it.
might not like it, or you might not understand it.
Okay.
Who is Squidward's favorite rapper?
I hate you so much.
You jerk. Someone got that? Someone wants to fuck
I really just
Ew.
sometimes I look at you and I wish I was blind.
Come on, that's like so great.
Wonder how much of this you can hear at home.
You know what, Andrew? The Packers still lost.
Okay. So, let's talk about physics.
You jerk.
All future was good.
Old Future's way better. That's facts.
Hopefully you wrote this down already. We talked lots and lots about elevators. You have a net force up when you're in an elevator, and it accelerates up. And you have that net force up because, I mean, we spent all of the last class period drawing those elevator force diagrams. And we know that when you accelerate up, you feel heavier than normal, which means you have a bigger normal force. Normal force is basically a measurement of how heavy you feel. So if that's true, if your normal force up is bigger than your force of gravity down, why don't you start, like, levitating in the elevator if that force is bigger than your downward force?
Oh,
It's kind of an interesting question,
I
isn't
never
it?
really thought of it like that.
Because, again, it's like you're here in your elevator. Gravity down is this size. You feel heavier, so normal force is like that. Doesn't this mean you should be, like, levitating and going upwards?
Gravity's pushing you.
It is, but I mean, gravity's smaller than your upward force. It's a tricky question. The answer is just the elevator moving up is what's causing you to have a bigger normal force in the first place. Your normal force is a reactionary force. Go ahead and just write down the normal force is a reaction to the elevator going up. The normal force is a reaction to the elevator going up. So it's not really you that's providing this bigger normal force, it's the elevator that's providing it. And you feel it as a reaction to the elevator accelerating up. The elevator accelerating up is what's accelerating up, not you. You're just feeling the reaction to that. Okay, we're going to take some short notes and then a couple other things today. Go ahead and get something out to write with and something to write on.
some of the feet.
There's a lot of V's up there. You're right. So, we've already got our hands full with equations. We've been dealing with a lot of them, and if you look at your formula sheet, there's even more than the ones that we've already dealt with. You know, in the motion box, you've got 8 different equations on there, right up here. And we've only dealt with about 6 of them. So what I'm going to do is I'm just going to quickly introduce you to the other 2. We'll practice a little bit, and then we'll get you going on the homework. So I gave you worksheet number 1 last time. Remember, that's due tomorrow. Today, I'm going to give you worksheet 2 along with a good start on it, and that'll be due on Wednesday. So, one of the x equations that we're familiar with is this one, x equals vt. We use this equation whenever we have a constant velocity in order to solve for position x. We're also used to this equation, a little bit anyway. We have to use this long position equation to solve for distance if we don't have a constant velocity. If we have an acceleration, it's taken into account in this equation. So that's something we use for more difficult circumstances. So those are our position equations. We're familiar with pretty much 2 velocity equations. Velocity is equal to distance over time, that's one. Or change in distance over change in time, sometimes it's written. The other velocity equation that we're familiar with a little bit is this one. Original velocity plus final velocity divided by 2. That would give you your average velocity. So we could put a little average sign up top if you wanted. But these are the 2 velocity equations that we've touched on at least once or twice. We also have 2 acceleration equations that we need to make sure we're aware of. Acceleration is equal to change in velocity over change in time. That's one of them. The other one is simply, remember the equation F equals ma? Yeah. We're kind of used to using that one. So if we would take F equals ma and solve it for a, we divide both sides by m, and a then is equal to F over m. So this is just kind of a running list of equations that we've played with. I'm going to introduce you to 2 more today, and these will be the last 2 equations that you'll be introduced to in this class.
Wow.
Yeah.
Really?
Yep. And this is the chapter that we're using these in right now. This chapter is not meant for it to be a really in-depth study of these equations. We're just starting to learn how to use them, so I try and hold your hand a little bit on in terms of when to apply them. So the same thing's going to be true with these 2 here. So another equation for velocity is this one. And these are all on your formula sheet. But one thing I've found is that the more you write these down, especially at the beginning, the quicker they're going to get into your head and not leave. So this equation is solving for final velocity. If you have an original velocity and you know your acceleration and you know your time, it's basically the same equation as this one. If I were to rewrite this equation here, a equals final minus original velocity over time, it's basically solving this for final velocity. So in reality, it's not a new equation, but it's a new way of looking at it. The last equation that I'm going to introduce you to is this guy. And you're going to put a little square next to both the first letter and then that one right there too. Now again, there will be a point where you do have to look at these equations and figure out which one to use, but that's not this chapter. This chapter, we're using them so that we can kind of get a feel for them in addition to going back to our force diagrams. Now, this equation would be good if we're looking for final velocity and we've got acceleration and we've got time. This equation right here, though, is a very, very special one. It stands apart from most of the equations on this list here. Anybody have a guess as to why it stands apart? Yes?
Because you gotta like do something with it afterward. Because you can't have like the
Oh.
velocity squared.
Well, that's true. That's not what I'm looking for, but that's true. It's the only one where you've got something different out here except the actual letter. Try and look at what's not present in the equation. Time, yeah. So what this means is that this equation is one we can use to solve for velocity if we have no information at all about time. If all we have is acceleration and the distance traveled, this is where we're going to go. And any time you are not given time in a problem, you're going to want to jump straight to this guy. So always check to see if it gives you any information about time. If it doesn't, you're going to have to go here. And I mention this so forcefully because this equation oftentimes gets forgotten about. So try and put this in the front of your brain because it comes in real, real handy. Questions on this list of equations here? Okay, so what I'm going to do next is pass out the next worksheet. We're going to go through a couple together, and then you should have a good amount of time to either finish up worksheet 1 or get going on this one. Yeah, that's good. I've also been thinking about the bridge project, and I kind of think it might be a good idea this year just to make it for extra credit.
Oh, thank you.
You're welcome. It's kind of a strange year. You know, some people are hesitant to go into stores and all that. And we certainly won't be able to test it the way we normally do. So, if you do want to make it, feel free to see me with any questions that you have. I know there's some people that really want to get on the Physics Hall of Fame, so feel free to continue with your work on that and see if we can get some more additions to that list this year. So, let's take a look at worksheet number 2. So worksheet 2 says, begin each problem with a force diagram. Some problems will need more than one. So let's take a look at number 2. We'll go through that one together, and then I'll give you a couple of hints about some other ones on the front. We'll take a look at the back. Make sure that's turned down. Thank you. Number 2 says the maximum force that a grocery bag can withstand without ripping is 250 newtons. Suppose that the bag is filled with 20 kilograms of groceries and lifted with an acceleration of 5 meters per second squared. Does the bag rip? So, with any of these problems where you need a force diagram or a force equation, it's always best to just start there. Instead of thinking about how you might solve this problem, always start it with a force diagram, follow it up with a force equation, and from there, it's going to be real easy to get to the solution. So, for this grocery bag, we've got gravity going down. We've also got normal force going up. Now, if you're the groceries in this bag, and this person is lifting you up, are you going to feel heavier or lighter than normal?
Later.
You'll feel heavier, just like when you get on an elevator and it accelerates up, you're going to feel heavier there. Same thing would be true if you were present inside a grocery bag. Your normal force would be larger then. Now our force equation, all the forces up minus all the forces down. Whoops, not 0. In this chapter, our equation is always set equal to MA. That's what we do here. So, the question is, does the bag rip? So, are we going to use this equation to figure out force of gravity or normal force to see if the bag rips? Normal force, exactly. Because when you lift the groceries, they feel heavier or lighter based on, how quickly you lift it up. So that normal force is what's going to cause the bag to either rip or stay intact. Now, force of gravity is its own thing, but however heavy these groceries feel when they're at rest doesn't really matter for the situation we're describing. So we want to figure out normal force here. So we just isolate it in the equation. We're going to put Fg over to the other side, and that's going to make it positive. In addition, force of gravity, remember, is just mg. So when we move this to the other side, it'll be plus mg. And now we can go ahead and solve. So 20 kilograms of groceries lifted at 5 meters per second squared. Then we've got mg here, mass. G is 9.8 on Earth. So when we do all this math, we're going to get a normal force of 296 newtons. So, does the bag rip? Yes, because this is going to be bigger than what the bag can withstand at 250. So when you lift it that fast, that bag feels heavier than 250 because its normal force is bigger than that value. 20 times 9.8 would be much less than 250. That's going to be a little bit less than 200 newtons. So if the bag was just sitting there and you didn't lift it up real fast, it wouldn't break. But because we're lifting it fast enough, it does. Questions on this one? Okay. That's kind of how the front side goes here. Number 1 is very similar. Number 3, there's a lot of numbers in this one. Go ahead and circle the number 840 in number 3 there. So that's what this student's weight is when he's at rest. So is that going to be a normal force, or is that going to be a force of gravity? Gravity, because he's at rest. So you might want to just put a little Fg next to that. Then, of course, you can see the other numbers. His weight increases to 1050, for an example, and then a little bit later on, it drops to 588. What are those? Force of gravity or normal force? Those are normal force, yeah, because they show how his weight changes based on what the elevator is doing. He feels heavier for the 1050, and he feels lighter for the 588. So those numbers will be normal forces in this one. And you'll solve those much the same way, except you're looking for acceleration instead of normal force. Number 4. For number 4, one of the things that you have to do is you're going to have to calculate force of gravity. And remember, force of gravity is equal to mg. And in number 4, you've got 2 separate masses. You've got the people, and you've got the mass of the elevator itself. So your mass in number 4 is going to be a combination of those. So there's 4 people in the elevator. There's 70 kilograms each. 4 times 70 is going to be 280. So there's 280 kilograms of people in there. The elevator itself is 500. So when you add those together, you're going to get a total mass of 780. And you'll use that to figure out your force of gravity. This, of course, is 9.8. So I just kind of wanted to get you started on number 4 there. The only other thing with number 4 is you're not dealing with a normal force in this case. You're dealing with a tension force. So usually in our examples, we come from the perspective of people who are either being accelerated up and down, and we say force of gravity down, normal force up. But in this case, we're dealing with the tension force of the string that's actually pulling these people up. So instead of being a normal force, you can think of this as a tension force. Still going up, you'd still treat it the same way with the force equation that you would a normal force. But yeah, just wanted to make you aware of that. Questions on page 1. Okay, let's take a look at page 2. We'll do number 5 together. All right, you guys are going to have a good amount of time to either get finished with worksheet 1 or get a real good start on this one. That's great. What's that? Yeah. So let's take a look at number 5. We've got ourselves a race car. So let me draw an amazing race car here. My wonderful artistic ability. Well, that's better than the one from the last physics class I drew.
A bit of drawing.
Shut up, Keegan.
Oh, so you can say shut up, Keegan, but I can't?
Yes. So this race car has a force of gravity down. It's got a normal force up. And if we're thinking of, what's going on horizontally, we could say it has an applied force because the engine is what's making it go forward. It's providing the push necessary for the car to go that way. And we'd have a really small force of friction going opposite. So this is what our force diagram would look like in this case. Now, it says right on top, we're going to have to use kinematic formulas as well as Newton's second law. And those kinematic formulas are the ones I was pointing at earlier in your motion box. There's 8 of them. These are the ones you're going to have to look at. Now, like I said, this is not the chapter where you learn how to deal with those from that, just without me giving you too many hints. I want you to just kind of see how they work in the chapter we're in right now. So, I'm going to give you hints on which ones you need for which problems. For number 5, we're looking for net force here. Now, let me just quick give you a description of what net force is. We've talked about force a lot. What net force means is it basically means the overall force. What is the overall horizontal force that this car is experiencing in order to cover 40 meters in 3 seconds? So let's pretend, just for right now, that the applied force is 5 newtons to the right. And let's pretend that friction is 1 newton to the left. My net force would be 4 newtons to the right. That's what net force is. It's your overall, after you've added and subtracted all the forces together, what's the overall force left over? And in this case, it's 4 newtons to the right. So, when it's saying net force, it's not specifically asking for the applied force or the specific force of friction. It's just an overall number that the force would be equal to in the direction of the car's motion. So, net force is equal to MA. In this picture, my net force would be applied force minus friction. But because we're just looking for that overall force from the beginning, we can just say net force equals MA. So, let's solve for it. We're given the mass, 710. Of course, we're not given the acceleration. So we got to figure what that is. So it says the car starts from rest, travels 40 meters in 3 seconds. So somehow I got to find an acceleration from this information. Now, I'm given a distance, and I'm given a time, and I'm looking for acceleration. So my mind goes to this guy. And you'll learn how to figure out which equation to use later on in the semester. So it doesn't say anything about not starting at the origin. So this is nothing. We're starting from rest. That goes away. So it's just distance x equals 1/2 at squared. So I know what x is. My distance is 40. It says that. My acceleration is what I'm looking for. And my time is 3 seconds. 3 squared is 9. So that's the equation I have. And I can just solve this equation for a. So 40 times 2 divided by 9 you'll get an acceleration of 8.89. So of course, in order to get your net force then, you take that acceleration, bless you, and you throw it back in up here for the acceleration. And then you'll get your final answer, which should be about 6,310 or so. Of course, remember I round my numbers to 3 digits, so this might not be a 0 when you plug it into your calculator. That's fine if you want to be more specific. And that's how number 5 would work. Questions on this? Okay. I'm going to give you a couple hints on some of the rest of these. Number 6, the equation that you want to use to figure that out is this guy. So this is a hint for number 6. Again, on the formula sheet, this is a y. That's simply because usually, overall in class, we use this with vertical motion more often than horizontal. But because we're doing introductory stuff here with this, this is how it would look for horizontal motion. So you're going to use that somewhere in number 6. You're also going to use this equation in number 6 because you're going to need to get an acceleration. So you're going to have to use that equation to figure out A. Number 7. Same equation. I'm just listing it as y right here, though, because in number 7, it actually is a vertical version of this equation. And that's what we usually see with it. So use that to figure out number 7. In terms of number 8, you'll need to use this guy. Oh, sorry. Thank you. It's Monday. So number 8, you'll have to use this guy right here. You'll also have to use this again. hopefully that's enough to get you going on worksheet number 2. That'll be due on Wednesday. And I'll get that out to you. I did hand that to you. Good. That should be it for today then.